Right. Good morning, guys. So welcome back to the fourth session of Diverse Note Mobility Front End Development Program. Today we will discuss Module 5, and that talks about arrays versus structures and the different aggregates for different purposes. So in this module, we will learn about, just wait for a minute, I'm going to share my screen to you. So here, yes, right. So here in this module, you will learn about array indexing using pointers, perils, and disadvantages, the void type, arrays, and multi-dimensional arrays. So memory and also memory allocation and the allocation and the malloc, open and close parenthesis, and free, open and close parenthesis, function. And also arrays of pointers versus multi-dimensional arrays, and also the structures, and also declaring using initializing structure on how to declare and how to use and how to initialize structures. And also we will also discuss pointers to structures and arrays of structures. So, and also lastly, the basics of recursive data collection. So let's have our first slide here. All right, so here, uh, indexing versus pointers. So earlier we were talking about tables, but we didn't say much about indexing. Let's summarize what we've learned so far. Consider the following declarations. So here in the snippet, here the declaration is char, then word, 10, and dump. So as we discussed in the previous lesson, that this is array. Right, so we have char type, and the value of the array is dump. Right, so we have created the 10 element array of a char or character and put a string dump there. Eventually we consume 5 chars of the array. So word 1, or the first element, would be A here, and puts word. So this is another declaration. So note that we've used apostrophes, not quotes. So don't forget, we will add apostrophes if it's char, and quotes if it's char and then asterisk. Right. So what's the difference between this one? Because this is a string, or this is a group of character. Because when we say a character, this is only one, just like this. So if this only one, so that would be a char. So we will add single apostrophe, or apostrophe, not quotes, because quotes is a single quote. Yeah. Right. So assuming that the following two statements have already been performed, we can guess that the word dump will be sent to the screen. It's clear to us that the appearance of the array's name followed by a pair of brackets means that we want to access, to get, or to modify only one of the array's elements, the one with the index equal to the calculate value of the expression enclosed in brackets. All right, so let's have here what will happen if we do something like this. Okay, so here in the declaration we have a word and -1 equals x, then word 1 million equals y. We can tell you what won't happen for sure. So the compiler won't signal either an error or a warning. And also the string contained in the array will not be changed. So that will be happen if we write this code. So what will be the effect of either of these assignments? Unfortunately, we can't predict with absolute certainty that what will happen. Depending on your compiler and or operating system, your program may continue quite normally, or it may also terminate with a message indicating a memory protection violation. It is also possible that you won't see anything and the program will end normally producing results that would make much sense, but it's also possible that in a strange and magical way, some variables will have completely uh, schis- um, schizoid values. This will be due to the fact that the value uh, you want to be assigned to the array element has gone elsewhere. It's impossible to predict where it's been deployed, but certainly the potential consequence could be rather unpleasant. Unfortunately, the burden of responsibility of indexing accuracy falls solely on the programmer. If you're careless when dealing with indices, your program could fail and searching for the reason will be very time consuming. So far, we've treated the indexing operation as a natural feature of arrays, but now we will show you another. More surprising side of indexing. These well-known brackets are nothing but an operator. This operator has the highest possible priority. It is as high as the priority of the suffix increment and decrement operators. How does this happen? So let us uh, know why in the next slide. So let's consider the following expression. So here in the equation we have in this expression we have t I in the bracket. So this is an array and then equals asterisk and then t plus I. The C language standard says if any pointer is followed by an indexing operator like this, it's always taken as asterisk t plus I. And then in particular, this means that the following expression, seek an expression involving two arguments, word 1 is treated by the compiler just like this one. Okay, so that's the same. We need your attention for a second. We are now going to explain step by step what that assumption means and what consequences can result from it. So for step 1, the name word is interpreted as a pointer to the first element of the array. It can be illustrated as follows. So here, as you can see, this step 1, the name word is interpreted in the pointer. So for the first character or char is D, then U, P, M, and P, and then null or backslash 0. So that is how that was illustrated. This expression is how it does it it is illustrated. Okay, so let's have the next slide. Okay, for step number 2, the pointer is increased by one word plus 1. This means that the pointer is shifted toward the right by one element of the array. You can see that in the figure below here, you can see uh, the word plus 1. So the expression should be will be char word equals dump. So word plus 1. So we add a word plus 1. So it is you. It would start with you. The increased pointer So here in the pointer, increase to 1 is an argument increase 1 uh, character is an argument difference operator, which means that it's of type char, at least from syntactic and semantic point of view. It's also an L value. This means that this assignment is fully permissible. So asterisk word plus 1 is equals to A. The meaning of this assignment is exactly the same as the one here. So this is the same. All right. So for step 3, take a look at the expression. Okay, just take a look and observe. Can you explain why we use the parentheses? Are they necessary? Okay, so they are necessary, yes. They are due to the very high priority of the deference operator, which is asterisk. Okay, so they are necessary because of the higher priority asterisk. So we've removed the parentheses just like this one. What will happen now? Firstly, the value or the character, a character pointed to the word is the reference. Secondly, a value of 1 is added to the reference character, not to the pointer itself. So take note of the difference. That's not what we wanted to achieve. Now we are going to show you something intriguing. You should be able to check it yourself, which is much more interesting than reading about it. Right? So let's consider the following expression. This expression T array of ti and then it. If t is a pointer and I is an expression of type int, then ti is equivalent to asterisk t plus I. And then the value is commutative. So we can write the previous expression in the following way. So here, asterisk and then open and close parenthesis, I plus t. And then this also means that we are allowed to write the same indexing operation as I and then t. This brings us to this conclusion. The bracket operator is commutative. Really. The compiler doesn't care whether you write word 1 is equals to A or 1 word equals to A. The first version is used most commonly due to developers' habits and the convention used in other programming languages, and also because such notation is somewhat similar to classical algebraic standards. But they are the same. The compiler will read it the same in the same way. Okay, let's have the slide. We advise caution with constructing expression using the asterisk operator, since any lack of parentheses will be detected by the compiler as syntax flaws. Imagine a set of declaration just like this: char string bracket and then equals abc, char asterisk p, char c. Then now we set p to point to the second element of the array string. The recommended form of this array is as follows. So the recommended form of this assignment is this one. P is equals to string plus 1. So acceptable. Though less elegant, however, should some would argue clearer, is the following form. So we can have P is equals ampersand or end string and then 1. So the pointer and the p pointer will point to the second element of the array string. Look at the figure. So what would be the second element of the array string? It should be u, right? So here, char word 10 equals dump and then dump, dump equal null and then p, right? So p is equals and word then 1. So can you answer the question of the distinguishes the following two instructions? C is equals asterisk P plus plus, or P increments, and C is equals to open in parenthesis asterisk P and then increment. We can explain the first element is as if the following two disjoint instructions have been performed. C is equals asterisk P, then P increment. In other words, the character pointed to by P is copied to the C variable, then P is increased and points to the next element of the array. The second element is performed as follows. To the the second assignment is here. C is equals to asterisk P string and then 1 and then increment. The P pointer is not changed and still points to the second element of the array, and only this element is increased by 1, right? Imagine the following assignment. All right, so we have the assignment P is equals string plus 2, and P points to the third element of the string arrays. What happened now? So here in this expression, P negative 1 is equals to E. It looks suspicious because we've used a bracket operator for a pointer that isn't the name of an array. Is this legal? Can we do it? Yes, it is. And we can. The compiler threats this as normal and thinks that we're trying to do something like this. Asterisk P minus 1 equals E. So this expression and this expression, we can have those, we can have the first one and the second one, and the compiler will read that in the same way. We want to change the element located before the one pointed to by the P pointer. In effect, it leads us to the second element of the array. The entire expression is treated as an L value and is assigned the character E. Since we know that a pair of bracket is actually an operator, we need to update our priority table here. So here's another updated priority table. So as you can see, we have the postfix, which is the increment, eh, decrement, and also the brackets. And also here another prefix, the not, here another type, the size of, here's another variable, uh, the reserved keyword, which is size of, and also the binary and unary operators. Right, so here's the continuation of the previous uh, slide, which talks about pointers can be dangerous. What do you think? Pointers are an extremely flexible and efficient tool for processing arrays and are very often used to create complex data structures. If you use them wisely and with due diligence, they won't cause you any major problems. Used improperly and carelessly, they may create lots of terrible issues. We will show you some typical mistakes in the hope that it will help protect you against similar troubles. So mistake number 1, okay, used of an initialized pointer. So you make this mistake when you use a pointer which hasn't previously been assigned any useful value and doesn't point to an existing variable or valid memory space. The compiler is unable to detect the error because its nature is to reveal and at runtime only. Consider the following, the example provided in the editor. So strcpy will the current value of ptr. So here, to determine the location where the string specify the second parameter should be copied. So however, the ptr variable hasn't been assigned. So strcpy brings with trouble. So if we are going to run this one, since the PDR isn't assigned, so it will cost us an error here. So if I run this code here, uh, the console will say line 1 437 segmentation fault. So we should assign the variable PDR. So the other side of this same mistake, take a look at the code in the editor. We tried to dereference and initialize the pointer. This won't end well either. Why do you think so? All right. So it also caused us error because of this one. So the mistake number two, exceeding the size of the array. So this happens when you forget what the declared size of your array is. So look at the example in the editor. See, we told the compiler that the str array will contain 10 elements, and then recklessly told to place a much longer string in there. uh, your program may finish its work with a message about memory violation error, although if you're unlucky, the program will go further, but the results may have little in common with your intention. So let's try what would be the output for this code. So here we have welcome to Trouble Land. So instead of copying the string again, so um it is it the console only prints one. The one welcome to Trouble Land. Okay, so how about the mystic free number three, non-terminated strings. We have a 10 element array of of characters here. Unfortunately, we haven't put a null character anywhere inside the array, and therefore that string likely has no end. The strcat function will persistently look for the end of the string, and it will probably find one eventually. There's a good chance that there is a byte containing a zero somewhere in the memory, but more than likely not within the str array itself. So here, so it is a bomb. So how about not only vectors? We've assumed thus far that arrays consist of scalars, but in fact arrays can contain elements of a much more complex structure. Let's consider the case when an array elements are just arrays. Surprising? Not at all. We often find arrays like this in our lives. Probably the best example of this is simply a chessboard. What we're going to say now will probably outrage experienced chess players, so we apologize in advance for our simplification and inaccuracies. If you're a chess player, it's nothing personal. A chessboard is composed of rows and columns. There are 8 rows and 8 columns. Each column is marked with the letter A through H. Each row is marked with a number from 1 to 8. The location of each square is identified by letter digit pairs. Thus, we know that the bottom right corner of the board is A1, while the opposite corner is H1. Let's assume that we can use the selected integer value to represent any chess piece. we can also assume that every row on the chessboard is a vector. So let's try to declare here it is. So here we have int row and then 8. So this is an array. Unfortunately, we have 8 of these rows. Does this means that we have to declare 8 arrays like this? Like int row 1, 8 row 2, 8 row 3, 8 until row 8, 8. So do you feel some sort of deja vu? We've already gone through a similar dilemma when we were trying to figure out what the reason for using vectors. Chessboard is in fact an eighth element of an array of element as single rows. Let's summarize our observation. So the first observation would be elements of rows are filled element 8 of them per row. So elements of the chessboard are rows, 8 of them per chessboard. So we are ready now to create an array for the chessboard. Here's the declaration. So we have int type, int chessboard, and then 8, and then 8. So the chessboard variable is a two-dimensional array. It's called by analogy to algebraic terms as matrix. Right, so the appearance of two pairs of bracket tells the compilers that the declare is not a vector, is an array whose elements are vectors. Access to the selected field of our board requires two indices. The first selects the row, the second the field number inside the row, which is de facto, and column number. So look at our chessboard. Every field contains a pair of indices which should be given in order to access the field's content. Glancing at the figure here, we can set some chess pieces on our board. First, let's put all the rooks on the board. So here, chessboard 00 and equals rook. Chessboard 07 equals rook. Chessboard 70 rook. Chessboard 7 equals rook. We wanted to place a knight on c4. We would do this as follows. So here, chessboard 3-2, we have knight, and now a pawn to e5. So chessboard 4-4 equals pawn. As clear as checkmate, right? So here, this is equivalent to the rows and the columns represented by alphabet and numbers. Now, let's go deeper into the multidimensional nature of arrays. To find any element of a two-dimensional array, we have to use two coordinates, a vertical, which is the row numbers, 1, and a vertical column number, 1. Imagine that we develop a piece of software for an automatic weather station. The device records the air temperature on an hourly basis and thus it's throughout the month. This gives us a total of 24 times 31 is equals to 744 values. Let's try to design an array capable of storing all these results. First, we have to decide which data type would be adequate for this application. We think that a float would be the best since our thermometer can measure the temperature with an accuracy of 0.1 degrees centigrade. Then we decided the rows will record the readings every hour on the hour. So the row will have 24 elements and each of the rows will be assigned to one day of the month. So we need 31 rows. Here's the appropriate declaration. Float, and then temp, 31, 24. So we have the float type because we will use some non-integers with or we have a point float pointing numbers here. So we will use a float type. So we have temp variable, and then this is array, which is composed of 31, 24 rows and columns. So now we will try to determine the monthly average noon temperature. We will add all 31 readings recorded at noon and divide the sum by 31. We assume that the midnight temperature is stored first. In the editor, you can find the relevant code along with the necessary declaration. So here's the code in the editor. As you can see, guys, that this code prompt as an error because this is not a whole code. We don't have return zero, the closing, and we don't have the header. But this code will represent this kind of equation that we have discussed earlier. So now let's find the highest temperature for the whole month. See the code in the editor. So here in the editor, as you can see, we have the flow type temp 31, 24, and we have integers day and hour. We have float. Let's have the assignment. Float max is equals to negative 100.0 and 4. We have the for loop here, which is days equals to 0 and days is we have days less than 31, then day increment, and then another for loop inside a for loop is for r is equals to 0, r is less than 24, r, and then increment r increment. We have if else conditional statement. So here we have declared temp inside, we have temp and then day hour is greater than max, which is max is equals to a temp, day, and hour. So we will the output will print as the highest temperature was float, and then the variable of the output should be max. All right, so we have another code here, and we want to count the days when the temperature at noon was at least 20 degrees Celsius. So we have declared flow type here, temp 31 and 24, int day and hour, int hot days equals to 0, and for loop here we have days equals to 0, and then day is less than 31, and day increment, and then we have if conditional statement here, and temp day and 11. So this number is an array and greater than or equals to 20.0 hot days increment. So we have to print f and then d, and then days were hot. So hot days. So the hot days is the variable. All right, so we use percent %d since we are talking about integer, and hot day is an int type or integer type. All right, so we're going to fill the entire array with zeros to prepare it for use in the coming month. So here is the example a code for this expression. Float time 3124 int dh, which stands for day and hour, and we have for loop, and d is equals to 0. D is less than 31. D increment for another for loop, and we have h is equals to 0, and h is less than 24, h increment, and then we have an array temp dh is equals to 0, point 0. So we are looking for the float here, which is equivalent to temperature. And the C language doesn't limit the size of the array's dimensions. Here we show an example of three-dimensional array. Now imagine a hotel. It's a huge hotel consisting of three buildings, 15 floors each. There are 20 rooms on each floor. We need an array that can collect the process information and the number of guests registered in each room. Step 1. The type of the array's element we think an int would fit, although it can be an assigned as there's no such thing as a negative number of guests. Step 2. Calm analysis of the situation. Summarize the available information: 3 towers, 15 floors, and 20 rooms. Now we can write the declaration as int gas 3, 15, 20, 20. The first index 0 through 2 in selects one of the building. The second is 0 through 14 and then selects the floors. The third is 0 through 29 and selects the room number. um, so it talks about elements and indices. And now we can book a room for newlyweds in the second building on the 10th floor, room 14. So we have guests 1, 9, 13, and 2. So what do you think it declares as this expression? Uh, we have two newlyweds, and then in the second building, so we are talking about the indices and elements here. So it is 1, and we have 10th floor. So we have 9, and then room 14, which is 13 in the elements and indices. So and release the second room of the on the 5th floor located in the first building. So we have in the second room on the 5th floor. Okay, this expression was just was just interchanged because the second room, because room talks about in the third number of the array, which is 1. Here, as you can see, in the first number talks about a building, and this one is the floors, and this one is the room. So we have in the second room, in the fifth floor, which is 4, and then the first building, which is a 0. So here, before we say goodbye and finish this part of our course, let us check if there's are any vacancies of the 15th floor of the third building. So we have int room. So we have a declared integer type, and the variable of that is room. We have int vacancy is equals to 0, and we have for loop, which is room is equals to 0, and then room is less than 20, room increment, and we have a if conditional statement here, and that is We have parameters gas to 14 room and equals to 0, and then vacancy increment. So the vacancy variable contains 0 if all rooms are occupied, otherwise it will display the number of available rooms. Right, so let's have the void. As we all know that the void is a reserved keyword, and this keyword is very exceptional type. We've seen that unusual type called void in our example a few times. We use it to indicate that the function doesn't return a result or doesn't expect any parameters according to the following function prototype. So here we have void, nothing at all, and then parameters is void. So the function should be invoked without parameters and return no result. This is how we should invoke it. Nothing at all. Then close and open parentheses without any parameters. Despite the factors that the void type doesn't represent any useful value, you can still declare pointers to this type, as in the following example. So we have void and then asterisk PDR. So you may ask how to use a pointer that points to nothing and ask so you may ask how to use a pointer that points to nothing and ask what such a pointer may be useful for. This kind of pointer, which is precisely of the type void or asterisk, is called an amorphous pointer. Take note of that to emphasize the fact that it can point to any value of any type. This means that a pointer of type void asterisk cannot be subject to the reference operator. So you must not write anything like this asterisk PDR is equals to 1. So it can be justified by the argument that if PDR was of type void, asterisk PTR would be of type void, and the assignment of a value of type int is prohibited by the compiler. However, pointers of type void asterisk are very useful when you need to have a pointer but don't know what you're going to use it for in the future. As soon as you know, the pointer can easily be converted into another pointer of the desired type. Of course, a pointer will. A trick that always possible and doesn't cause any loss of accuracy. All right, so that is the pointer void, and that is called amorphous pointer. So let's have the memory allocation and the allocation, or its reserved keyword. Its keyword is malloc, open and close parentheses, and free, open and close parentheses. So memory on demand. In the examples we've shown you so far, memory management has taken place outside of our awareness. So the parts of the memory which we've used to store values have been hidden behind the names of scalars and arrays. They appear as soon as they've been declared and disappear when our program ends its operation. All work associated with memory allocation has been organized by the compiler, and we haven't care about how it works. This is how it should be. High-level languages and their compilers are designed to exonerate the developer's mind of this mundane task. But very often the developer wants to have full control over how much memory is used and when exactly it is used. This is especially important when you don't know in advance what the size of the data to be processed in. To manage the allocating and freeing of memory, the C language provides a set of specialized functions. Here we will use two of them, and we don't need to go into too much depth because you just need to understand the main rules. Using both functions, however, requires the inclusion of the header file stdlib or library.h. The following function is used to request access to the memory block of a specified size. The operating system can react in two ways. It either finds that there is free memory that could be given and our request is granted, or if the system is suffering from a shortage of memory, our request will be denied. When the allocated memory is no longer needed and or utilized, it would be a good idea to return it to the operating system. We do this by using the second of these two functions. So the function that performs the first task has the following prototype. So we have void, asterisk malloc, and then int and then size. The name of the function is a conflation of memory allocation. Its only parameter provides information about the size of the requested memory and is expressed in bytes. The function returns a pointer of type void asterisk which points to the newly allocated memory block or is equals to null to indicate that the allocation requested could not be granted. The function doesn't have a clue as to what we want to use the memory for, and therefore the result is of type void asterisk. We will have to convert it to another usable pointer type. The allocated memory area is not field initiated in any way, so you should expect it to contain garbage. The function invoked when the memory is no longer necessary as the following prototype. So we have void free and then close parenthesis, void, open parenthesis, a void asterisk pointer and then close parenthesis. The function name doesn't require any comments. The function does not return any result, so its type is defined as void. The function expects one parameter, the pointer to the memory block that is to be released. Usually, it's a pointer previously received from the malloc or memory allocation or its kindred. Using another pointer value may cause some kind of disaster. The function doesn't need to know the size of the freed block. You can only release the entire allocated block, not a part of it. After performing the free function, all the pointers that point to the data inside the freed area become illegal. Attempting to use them may result in abnormal program termination. Now, a few words about the pointer type conversion issue. Well, it's performed in a way we're already familiar with using the conversion operator, also called typecasting. Converting from void asterisk to another pointer type always requires explicit typecasting. Transforming from any pointer type to the void asterisk type doesn't require explicit typecasting. So typecasting is when you when the code is performed and with using the conversion operator, and that is called typecasting. Conversion operator. We're going to show you a complete, although not useful, program that demonstrates the use of both functions. We declare the variable called PTR, which will point to the data of type int. The pointer type is int asterisk. Initially, we assign no value to this variable. We invoke the malloc function requiring the allocation of a memory block sufficient to store one value of type int size of int. This enables our program to correctly execute regardless of how many bytes are utilized by int type in the specific implementation of the language and or hardware platform. The malloc's return value is assigned to the PTR variable using typecasting converter, converting the pointer of the void asterisk type into an int asterisk type. We need to check the resulting pointer value. If it's not null, it can be safely used. Our program assigned a value of 200 to the allocated memory, prints the value using the printf function and frees the memory. If the memory allocation goes wrong, malloc returns null and we do nothing but print an error message. So since we are going to use malloc and free function, so we add a header in hash include std like dot h, and we have a main function here in main void, and we declare int a pointer asterisk pdr, and we have the value of pdr equals int asterisk malloc size of, and then we have the parameter int. So we have an if else statement, conditional statement here. So if it's if, then we have ptr not, if pointer is not equals to null, and then we have the pointer is equals to 200, then we will have to print ptr values of a value of integer, which is the pointer is 200, and that would be here, and we have the free ptr. Or else if this conditional is false, then it will print as allocation fail. So as we run this program, we will get a result of ptr points the value of 200. So this conditional statement is has already run with this with the compiler. So the option of allocating the amount of memory that we really need lets us write program that can adapt themselves to the size of the data currently being processed. Let's go back to the bubble sort algorithm that we looked at some time ago. That program assumed that there were exactly 5 numbers to sort. This is obviously a serious inconvenience. It may happen one day that, oh, we want to sort 10,000 numbers, or maybe even hundreds of thousands of numbers. What then? You can, of course, declare an array of maximum predictable size, but it would still be inconvenient. A much better way is to ask the user how many numbers will be sorted, and then allocate an array of the appropriate size. Let's try to start with a simpler example. In the following program, we allocate an array containing 5 elements of type int, and set their values, sum them up, and finally release the previous allocated memory. As you can see, we've done quite haphazardly and haven't checked if the memory allocation has succeeded. It can omit in a program like this, but when we perform more complex tasks, we need to verify it. So we want you to pay attention to the fact that the pointer returned by malloc is treated as if it is an array. Surprising. The handling of dynamic array created during the run of the program is no different than using regular array declared in the usual way. We owe it to the bracket operator. Regardless of the nature of the array, we can access its element in the same way. So here in this code, guys, written in the editor, so that is the code that was uh, the codes or the statement that is described between these lines. So we are going to make this run. So we are going to put header and just create a function or the main function and just add return 0. So we will just add include, and then stdio dot h, and then hash include std lib.h. Then we should enclose them in the main function. We will have void parameter, and we will just add curly bracket, and then just add return 0, and then close curly bracket. So if we are going to run this one, so we will just create it will just pop up a success, and it's the console have no result for this one, since it is just a void character, and we only just created a logical way on how this equation to write in the statement form or in the source code form. So let's have another one. The improved bubble sort program is in the editor. So now we'd like to draw your attention to the following scanf function call, and we have the scanf percent %d, which is represent for integers, and we have the variable number plus I. You should be able to begin the meaning of this invocation and why we use the class number plus I here. So here in the editor, as you can see, we have the bubble sort program. And the first thing that the program will ask you is how many number are you going to sort. So if we are going to run this one, and the console will prompt us how many numbers are we going to sort. And then as you can see, we have the scanf %d and how many numbers. And so we have the if else statement here. Oh, here we have how many numbers less than equals to 0, and then this one, or how many numbers is greater than uh, 1 million, and then printf, are you kidding? Okay, so let us try that. If that that statement, conditional statement, will run. So let's have negative negative 1. So let's have -1. All right. So it prompt us. Are you kidding? So let's have the next if condition. So numbers is equals to null, then allocation failed, then sorry, return 1. So let's have for loop. This is another loop inside the if else not null, and then if conditional statement numbers equals null. So we have the for loop I is equals to 0, and then I is less than how many numbers, and then I increment. So we have print enter number, and then here's the this is just a new line. All right, so I then +1, so it will just prompt us here. I have tried it earlier. Right, so how many numbers are going to sort, then 3, and then here enter the number 1. So here I'm going to the enter number 1 is came from this statement print f enter number, and then scan f, and then it will scan after I enter some number here, and if I already enter, it will do this loop swap 0, and then I is equals to 0, and then uh, I is greater less than how many numbers, -1, and I plus plus, if then this one is the logic from, or the code for swapping or the sorting of the numbers. And then while swap, then print f the sorted array, and then right. So let's have the full example here. So I have how many numbers are going to sort the 3. Right. So the first number, I would like it to have the value of 12. Number 2 will have 1, and then number 3 will be 9, right? So one more time. This compiler is such is quite different from the other, since the entering of the value exceeds from the runtime limit. So we should lesser than 0. Right, so this is the sorted array. So guys, this for the module 5, this fourth session will end for now. This is just a part 1, and look in the next video for part 2, module 5. So, sorry. So this concludes the fourth session, part 1 of the diverse node mobility front end development program. So see you guys in the next video, and hope you learn something in this course. Have a good day.